The global scale operations team realizes that their logistics AI is fragile. It works perfectly in calm, predictable conditions, but fails catastrophically under extreme stress. During a recent peak demand cycle, a minor sensor error in a warehouse caused the entire fleet logistics model to misinterpret the data, resulting in thousands of misdirected shipments. The head of operations, Marcus, declares that this level of fragility is unacceptable. He initiates a resilience initiative, tasking his team with creating a testing environment that can simulate the most chaotic, high pressure, and failure prone conditions imaginable. They recognized that their current testing regime was limited to happy path scenarios, completely missing the reality that AI must be able to handle extreme, unexpected, and even hostile inputs without collapsing. They decide to move beyond mere functional testing toward a more rigorous adversarial approach where they deliberately try to break the system in every possible way to identify its hidden weaknesses before they can impact real world customers. This marks the beginning of a transformation toward a more robust, battle tested, and truly reliable logistics platform that can handle anything the world throws at it. The team designs a stress test suite that pushes the logistics model to its absolute limits, simulating everything from sudden regional power failures and massive unexpected order surges to corrupted data streams and malicious adversarial noise. They create digital prints of their physical warehouses and transport networks, using them to run thousands of high-intensity simulations every hour. They define safety boundaries for the AI, establishing the exact performance limits where the system must trigger a safety intervention rather than continuing to execute potentially disastrous decisions. This is not about optimizing for speed, but for survival. The team spends weeks refining these scenarios, ensuring they are as realistic as possible, including everything from extreme weather to network latencies that could confuse a lesser model. They are essentially putting their AI through a grueling, high pressure training course that forces it to learn how to handle uncertainty, chaos, and failure. This process is essential for building a truly reliable, enterprise grade system that can operate safely in any environment, regardless of the challenges it faces. With the new stress test results, the team implements a set of fail-safe overrides into the model's core logic. These are automated, hard-coded safety rules that trigger if the model's performance deviates from its established safety parameters, forcing it into a conservative manual override mode rather than allowing it to continue making potentially disastrous decisions. This creates a safety net that allows the system to operate with confidence even when it reaches the edge of its capability. The engineers also build a predictive uncertainty monitor that tracks the model's confidence in its own decision-making process. If the uncertainty grows too high, the system automatically offloads the task to a human operator. This layered approach to safety, combining high-performance automation with robust fail-safe overrides, is the key to ensuring operational reliability. The system is finally becoming fail-aware, meaning it knows when it's struggling and knows how to gracefully hand off control, ensuring that safety is never compromised, even in the middle of a massive peak operational load crisis. The team conducts a massive company-wide peak load simulation, running the logistics model through the most intense and stressful scenarios they have developed. They observe the system under the equivalent of a Black Friday event combined with unexpected network outages and sensor malfunctions. To their relief, the new stress testing protocols and fail-safe overrides perform exactly as designed. When the model encounters a confusing, high uncertainty data stream, it instantly triggers the safety override, alerts a human, and successfully maintains stability until the situation can be resolved. The system doesn't crash, and it doesn't make erroneous, expensive, or dangerous decisions. This is the first time the company has achieved such a high level of operational confidence in its automated fleet logistics model. The test results confirm that the system is now truly enterprise hardened, proving that the rigorous investment in stress testing and fail-safe design has fundamentally transformed the company's ability to manage complex global operations under even the most challenging high-pressure conditions. The Operations Council conducts a formal audit of the new reliability framework, comparing the performance of the system against the pre-hardening version. The data is clear. The new model has a 99.9% reduction in catastrophic failure incidents and a significant improvement in overall operational uptime, even during periods of extreme high stress load. The audit validates that the investment in adversarial stress testing and fail-safe design was not just a safety precaution, but a major driver of operational efficiency and cost reduction. The executive team is satisfied with the results, noting that the new system is not just safer, but more reliable, more predictable, and better able to handle the complexities of global logistics. This audit success provides a final validation for the company's new principled approach to operational AI, ensuring that safety and reliability are at the core of all future AI-driven business projects, and reinforcing the company's commitment to building technology that is truly resilient, robust, and worthy of its customers' trust. Global Scale decides to formalize this resilience framework, establishing it as a mandatory standard for all safety-critical AI projects across the company. They create a resilience playbook that provides every engineering team with the tools, templates, and best practices for implementing adversarial stress testing and fail-safe design in their own projects. This ensures that the lessons learned from the logistics project are spread throughout the organization, turning reliability into a standard expected part of every team's workflow. The team continues to refine the simulations, incorporating new emerging failure modes and adversarial threats as they appear. They are now working on self-healing AI that can automatically detect, isolate, and recover from minor system failures, further improving the company's overall operational uptime. This marks the final step in the transition to a truly resilient AI-powered enterprise, proving that when companies treat reliability as a foundational, core governance requirement, they can build incredibly high-performing systems that thrive under any conditions.